Hello everyone, I'm Joachim Tapparel. I'm a PhD student at EPFL in Switzerland, and I'm working with the Telecommunication Circuit Laboratory. Today I will talk about the physical layer of LoRa, and hopefully at the end of this talk you will all have a good understanding of what makes a LoRa transceiver. Maybe not. Okay. So for those of you who don't know, LoRa is a low-power wide area network technology that uses the ISM, so unlicensed frequency band, to deliver a low data rate to many IoT devices. We are particularly interested in using GNU Radio for research purposes for us, because it enables the use of convenient software-defined radios. We can easily share what we do with other labs or other people, such that it doesn't get lost forever when we are done with the research we do. And LoRa is very well suited to be implemented in software-defined radio, as it uses small bandwidth and has no real timing constraint, or not stringent timing constraint. So it can run on a very inexpensive inexpensive hardware. So as an overview of what I will talk about, we can have a look at a block diagram of a transmitter. So some of you might recognize a lot of those words. It's a very simple bit interleaved coded modulation. So it's nothing too fancy, as it needs to run on low power IoT device. So the algorithm stays simple. Now, if we want to look at the receiver, it's basically exactly the same block diagram, but in the reverse order, where each of the receiver parts will undo what the transmitter did. And in today's talk, we will follow the trip of 1 byte of data, that will be all one, for the example, that go through the transmitter and receiver chain, and we'll see what happened to it. So the first operation we want to do is to remove any pattern of the binary values that is specific to what the user wants to transmit. And this can be easily done with whitening, so you can XOR your input data with a pseudo-random sequence, and you get a new sequence that looks much more random. Out of each byte of input data, you can create 2 nibbles, and we will use that to create a code word later. So you repeat that process or you continue that process for the full payload, and you get a bunch of data bits. You can prepend a header in front of it that will give useful information for the decoding, and append a cyclic redundancy check, which is some kind of hash to verify the data integrity at the receiver. Now we have all the contents, all the information bits that we want to transmit, and we will add some redundancy to it. LoRa uses a simple Hamming code to add redundancy, and you can see here the expression of the simple matrix multiplication that you can do with all your nibbles, and you get the code words you want to send. So that's the whole data we want to transmit in our frame. But instead of transmitting it sequentially, we want to distribute the bits of a code word into different symbols, such that if one is lost, then other symbols can help recover it. And LoRa is using a diagonal block interleaver, and it's given by either this equation that you can see on the slide, or intuitively you take the code block or the interleaver block, you rotate it by -90 degrees, and then each row you do a circular shift of each row, and now you have your interleave block. So now each bit of a code word lies in a different row. And each of those rows will give you decimal value or a symbol value you want to transmit, and it's using a simple gray code, such that every decimal value will have only 1 bit difference with the next value and the previous one. And now we have value we want to transmit, but we need to have waveform to be able to send it over the air. And one of the particularities of LoRa is that it's used chirp spread spectrum modulation. So you start at a low frequency, and during the time of a symbol, you will have the frequency that increases linearly. You can use that expression here to modulate a waveform with a value, and more intuitively, you change the starting frequency of the chirp, and that's where the information about your symbol lies. So here you can see a spectrogram of what we transmit over the air. Obviously here it's with a very high SNR, but that's what you will transmit. And now we can look at the receiver, how you deal with it to get back your information. For people that are attentive, you might have noticed I've swapped the block diagram on the top with a flow graph, because flow graphs are better, they compute something, so I just replace it here. Let's look how we demodulate the information now. So you have your chirp, so your received signal. If you do element-wise multiplication with a specific waveform, you will concentrate all the energy of a symbol into a single frequency. Then it's quite intuitive. You take the discrete Fourier of that new symbol, and it gives you a spectrum that you can see on the bottom right, where you have all the energy that is in one frequency bin. And luckily for us, the frequency bin in which it lies is the symbol that is encoded the value that is encoded in the symbol. And that's one of the key aspects of LoRa, is that you can get the maximum likelihood detection, but only with a complexity of n log n, because you can use the fast Fourier transform to perform all the correlation necessary. Now I was a bit optimistic because real life is not as kind. So instead of demodulating a symbol that looks like a Dirac, you will suffer from carrier frequency offset or sampling time offset every hardware impairment. And now it's more difficult to know which value of the output of the FFT is our symbol. So if you add on top of that you account for noise that is also added by your receiver chain, it becomes difficult to find where your symbol value is, and hits here. So it's not even the maximum now. So what you need to do is to estimate all those offsets and compensate them, which I won't give the detail now. But in short, you can have 4 different steps that you can follow to first remove some subsample offsets that will have the effect to gather back all the signal energy into one bin, and then you have integer offsets that you can compensate that will shift back the bin in its correct position. So now you get your sample value back. You can do that for your full signal, and you get all the value of all symbols. So you undo the gray mapping, you get back your interleave matrix, you deinterleave it by doing just the reverse as a transmitter, and you are back to having code words. And now it's the decoding, so it needs to be a bit more interesting, or it needs to do something, because we add redundancy for a purpose. And LoRa uses a simple Hamming code, so you can view it as a Venn diagram, where you get parity bit and data bits. You feed the bits in one COM word in this Venn diagram, and you can XOR all the elements in a circle. If they give you a 1, it means there is a problem. If they give you a 0, it means it's fine. And now we can see that there is a problem in your receiver. And one can notice that if you would flip this bit here, everyone would be happy. So it's very probable that this bit was flipped due to the wrong demodulation. So you can correct it in your data. And since we are decoding the first interleave block, we get back our header value. And in GNU Radio, you need that information to decode the rest of the payload. So you can feed it back with an asynchronous message to the beginning of the receiver chain, and then it gets propagated to each block that needs it via a synchronous tag. So for the payload, it needs to be de-whitened, which is exactly the same operation as the whitening. You XOR it with the same pseudo-random sequence, and now we can see our sequence of our original bytes being back. You compute the cyclic redundancy check on it, and you can compare it with what you received from the packets. And if it's correct, it means you have successfully decoded your packets. Now, I've talked about many blocks, and they are all available and implemented on our Git. We could evaluate if it was working not only in simulation, but also in real world, so with USRPs in our testbed to suffer from CFO and STO and observe the performance. And it has also successfully been used in many papers that deal with a lot of different topics. And I think that the presenter next to me also use it, so I'm eager to see what he will say about it. Now we are working on what next for our implementation. We are working on a centralized radio access network architecture, so having a distributed antenna array and then processing jointly the IQ sample received by the different locations. So we've built a prototype of gateway that is based on USRP and a Raspberry Pi. We've put a few of them on the roofs of the campus at EPFL, and you can see here a plot of the received SNR based on the position of the transmitter. So thank you for your attention, and if you have any question, I will also be around the rest of the week.